You are kneeling in the dirt roughly 8,000 years ago, somewhere in what is now southeastern Turkey. You have been hammering a rock for the better part of an afternoon. Not a normal rock. This one is different. It is heavy, oddly smooth, and it has a reddish color you have never seen in stone before. Every other rock you have ever hit either chips into a sharp edge or crumbles into dust. This one does neither. When you strike it, it flattens, it bends. It squishes like wet clay, except it holds its shape. You hit it again, harder, and the edge spreads thinner but does not break. You have no word for what this material is. You have no concept of metal. You have never seen anyone work with anything like this. But you can feel, instinctively, in the way the surface yields under your stone tool without shattering, that this is something new, something your stone cannot do. And that rock, that strange reddish lump you pulled from a riverbed or a cliff face, is native copper. And you have just become one of the first humans to work with metal. You did not know that. Nobody told you. Nobody could have. Because the discovery of copper is not a story with a single inventor or a single moment, it is a story that stretches across 10,000 years, at least 3 continents, and an accident so strange that scientists are still reconstructing exactly how it happened. So, how did humans figure out copper? The answer starts with a green rock, and it ends with the complete reinvention of human civilization. Let's start with what copper actually is, because most people think of it as a thing you mine. A raw material you dig out of the ground and smelt in a furnace. And that is true eventually. But the first copper humans ever touched was not smelted. It was not extracted from anything. It was just sitting there, on the surface, looking like a weird rock. Native copper is one of the few metals that occurs in nature in a pure metallic form. Most metals are locked inside ores, chemically bonded to oxygen or sulfur, invisible, completely disguised as ordinary stone. Copper is different. In certain geological conditions, pure copper forms as nuggets, sheets, and veins in basalt and sedimentary rock. It looks like metal because it is metal. And in the ancient Near East, particularly in eastern Anatolia, modern-day Turkey, and the Zagros Mountains of western Iran, chunks of native copper were weathering out of exposed rock faces and washing into riverbeds long before any human had the slightest idea what to do with them. And here's the connection to the question of discovery. Humans did not discover copper because they understood chemistry. They discovered it because they noticed it was strange. Every other rock breaks. This one bends. That is all it took. Curiosity about an unusual rock started the longest technological revolution in human history. At a site called Keonu Tepezi in southeastern Turkey, excavations dating to roughly 8,200 to 7,500 BC revealed that people were actively working native copper into small objects. Beads, pins, fishhooks, awls. They cold-hammered the copper nuggets, pounding them into shape with stone tools. No heat, no furnace, just muscle and repetition. And at some point, somebody figured out that if you put the copper in a fire and let it heat up, it became softer and easier to shape. That process, heating the metal and then hammering it, is called annealing. It sounds simple. It is simple. But it is also the first deliberate use of heat to change the properties of a material. And that is a concept that would eventually lead to every forge, furnace, and factory on Earth. Now, here's what makes the copper discovery story genuinely unusual. Those people at Keonu Tepezi were not metal workers. They were not miners. They were not specialists of any kind. They were early farming communities, some of the first settled agricultural villages in human history, and they treated copper exactly the way they treated any other interesting rock. They made beads from it, they wore it. They poked holes in leather with it, and they were not alone. At Ali Kosh, in western Iran, archaeologists found a single-rolled native copper bead whose style matches the ones at Keonu, suggesting that copper objects were already being traded between communities before anyone understood how to make more of the material. At Zawi Kemi Shanidar, near the famous Shanidar cave in what is now northern Iraq, copper beads and pendants turned up among early pastoralist groups dating to the 10th or 9th millennium BC. At Catalhoyuk, the massive Neolithic settlement in central Turkey, occupied from roughly 710 to 5700 BC, more copper trinkets, beads, small ornaments. Nothing that would change your life, nothing that would win a war, just decoration. And that is the part that matters for the discovery story. For roughly 3,000 years, that was all copper was. A shiny, bendy stone that made nice jewelry. Nobody looked at a copper bead and thought, this material will one day build empires. They thought, this is pretty. And they were right. It is pretty. It just also happens to be the gateway to the entire age of metal. Think about that timeline. 3,000 years of treating copper as decoration before anyone figured out you could do anything serious with it. For context, 3,000 years ago from today is roughly 1000 BC. The gap between first using copper and first smelting copper is the same as the gap between King David and your smartphone. That is how slowly this discovery unfolded, and the people who made that next leap from hammering native copper nuggets to actually extracting copper from rock did not do it on purpose. Here is where the green stone enters the story. Malachite. It is a copper carbonate mineral, chemical formula Cu2CO3OH2. It is a beautiful deep green, striated, sometimes banded with lighter and darker layers, and ancient people loved it. They loved it the way we love emeralds. Long before anyone connected malachite to copper, long before anyone understood that the two materials had anything in common, Neolithic communities were mining malachite across the Near East and grinding it into fine powder for eye cosmetics. The Egyptians used it extensively, but the practice is far older. They carved it into beads, they used it as pigment, they were stockpiling copper ore, unknowingly, because they thought it was a pretty green rock. And here's where the accident happens. And this is the moment that answers the question of how humans discovered that metal could be pulled from stone. Now, the popular version of this story goes something like this. Some ancient person built a campfire on a rock that happened to contain copper, the fire melted the copper out, and there it was. Metal sitting in the ashes. Great story. Not true. An open wood fire tops out at roughly 600 to 800 degrees Celsius. Pure copper melts at 1085 degrees Celsius. You could sit next to that campfire all night, and the rock would not give up a single drop of metal. The campfire theory is the kind of explanation that sounds right until you check the numbers, and the numbers say no. So if a campfire cannot do it, what can? A kiln, specifically a pottery kiln. Early potters had been building increasingly sophisticated kilns. By around 6000 BC, two-chambered kilns in the Near East were reaching temperatures above 900 to 1200 degrees Celsius. Those potters had also learned, probably by trial and error, that restricting the airflow inside a kiln changed the color of their ceramics. Less oxygen produced darker, richer colors. More oxygen produced lighter ones. They were manipulating what chemists call a reducing atmosphere, an environment low in oxygen, without having the faintest idea what oxygen was. There is also another possibility: lime plaster production. Making lime plaster requires heating limestone in massive kilns to temperatures above 900 degrees Celsius, and malachite, the green copper ore, often occurs geologically alongside limestone. If someone tossed copper-bearing rocks into a lime kiln, either as building material or by accident, the same reduction chemistry would apply. Andreas Hauptmann, an authority on early smelting chemistry, spent years studying ancient smelting residues in the Fainan district of Jordan, combining mining archaeology with lead isotope analysis to understand how early furnaces actually worked. His conclusion was that the transition from natural mineral to extracted metal happened gradually in fits and starts across multiple communities and multiple pyrotechnologies. It was not one eureka moment. It was a slow accumulation of accidental observations by people who were paying attention. Now, malachite was being used as a green glaze for pottery. You grind it into powder, coat your ceramic, and fire it. Beautiful green finish. But here's the chemistry. When malachite is heated to around 300 degrees Celsius, it decomposes into copper oxide, carbon dioxide, and water vapor. And when that copper oxide sits in a charcoal-fueled kiln with restricted airflow at temperatures above 800 degrees Celsius, the carbon from the charcoal strips the oxygen away from the copper oxide. What you're left with is pure metallic copper. Tiny beads of shiny reddish metal sitting in the bottom of your kiln or stuck to the surface of your pottery in a place where no metal existed before. Think about what that must have looked like to someone who had never seen smelting. You put a green rock in a hot fire, and a completely different material came out. Not green, not stone. Something shiny, heavy, malleable. Something that looked exactly like the native copper nuggets people had been hammering for 3,000 years. Except this time it came from inside an ordinary-looking rock. That is not just a discovery. That is alchemy. That is magic. And the fact that it was actually just chemistry made it infinitely more powerful. Because unlike magic, you could do it again. The oldest confirmed evidence of this kind of copper smelting comes from a site that surprises most people. Not Mesopotamia, not Egypt, Serbia. At a site called Belovode, near the Danube River, archaeologists Miljana Radivojević and Benjamin Roberts found copper slag, the waste product of smelting, dating to roughly 5000 BC. Slag is the proof that someone was not just melting native copper, but extracting it from ore. The Vinca culture, the people who lived there, had figured out extractive metallurgy entirely independently of the Near East. Colin Renfrew, the archaeologist who revolutionized the field using calibrated radiocarbon dating, had argued decades earlier that metallurgy was independently invented in the Balkans. Belevode proved he was right. Two separate groups of humans, separated by over 1,000 kilometers, both figured out that you could pull metal from rock. The chemistry demanded it. If you have malachite, charcoal, and a hot enough kiln, copper is going to show up eventually. It is not a question of if, it is a question of when. But smelting was only half the problem. Pure copper, even smelted copper, is soft, softer than a good piece of flint. You can hammer it into a blade, but the blade bends. You can shape it into an axe head, but the edge deforms after a few uses. Copper was beautiful. Copper was novel, but for the first few centuries of smelting, copper was not actually better than stone for most practical purposes. A well-knapped obsidian blade was sharper. A granite axe head was harder. Copper's advantage was that it could be melted and poured into a mold, creating shapes that stone could never hold. But in terms of raw performance, stone still won most contests. So why did copper take over? Because somebody figured out alloying. And the first alloy was an accident that killed people. Across parts of the Near East and the Iranian plateau, some copper ores naturally contain arsenic. When smiths smelted those ores, the resulting metal was not pure copper. It was arsenical copper. And arsenical copper is significantly harder than pure copper. It holds an edge better. It casts more cleanly. It was by any practical measure a superior material. By the 5th millennium BC, sites like Tepe-Sayalk in Iran were producing arsenical copper tools and weapons. Over time, some smiths appear to have begun deliberately mixing copper ores with arsenic-rich minerals, intentionally making the alloy harder. They were doing materials science 5,000 years before the phrase existed, but there was a cost. Heating arsenical copper releases arsenic trioxide gas. Breathing it causes respiratory damage, skin lesions, nerve degeneration, and chronic illness. The smiths who made these weapons were slowly poisoning themselves. Otzi, the Iceman, that 5,300-year-old mummy found in the Alps in 1991, had elevated arsenic levels in his hair, consistent with someone who spent time near copper smelting operations. And here is a detail that connects ancient metallurgy to ancient mythology in a way most people never notice. The Greek god of the forge, Hephaestus, was famously lame. He walked with a limp. He was physically deformed. For a long time, scholars treated that as a random mythological detail. But chronic arsenic poisoning causes peripheral neuropathy, nerve damage in the extremities that produces exactly the kind of limping, weakened gait that the myths describe. The god of metalworking was crippled by the materials he worked with. That is not mythology. That is an occupational hazard, remembered across thousands of years of storytelling. And while arsenic was quietly poisoning the first metalworkers, the solution was already sitting in the ground waiting to be found. Tin, mix roughly 90% copper with 10% tin, and you get bronze. Bronze is harder than arsenical copper. It holds a sharper edge. It has a lower melting point than pure copper, somewhere in the range of 900 to 1080 degrees Celsius depending on the ratio, which makes it easier to cast. And it does not release toxic gas when you work with it. Bronze is by almost every measure the superior material. And its discovery, around 3500 BC in Mesopotamia, and possibly as early as 4500 BC in the Balkans, launched an era so defined by a single alloy that we named 2,000 years of human history after it. The Bronze Age, not the Agriculture Age, not the Writing Age, not the City Age, the Bronze Age. That is how much copper alloyed with tin mattered. But bronze created a problem that pure copper never had. Copper ore is relatively common. You can find it across the Near East, in Cyprus, in the Sinai, in Anatolia. Tin is rare, geologically rare, and geographically concentrated. The nearest major tin sources to Mesopotamia were in Afghanistan, Central Asia, Cornwall in Britain, and parts of the Iberian Peninsula. To make bronze, you needed both metals. And that meant trade. Long-distance, organized, politically complex trade networks that stretched thousands of kilometers. In 1982, a shipwreck was discovered off the coast of Kos, Turkey. The Uluburun wreck, a late Bronze Age merchant vessel that sank around 1320 BC. It was carrying 10 tons of copper as oxide ingots, flat, roughly rectangular slabs weighing 20 to 30 kilograms each with four corner handles, the standard currency of bulk metal trade. The copper was Cypriot. But the ship was also carrying 1 ton of tin, sourced from the Taurus Mountains and Central Asia. One vessel, sitting on the bottom of the Mediterranean for over 3,000 years, carrying enough raw copper to forge 5,000 swords and enough tin to alloy it all into bronze. That is not a fisherman's boat. That is an industrial supply chain floating across the sea 3 millennia before containerized shipping. And here's where the discovery of copper connects directly to the invention of civilization itself, because copper did something that no previous material could do. It created specialists. Making stone tools is hard, but in principle, anyone can do it. You find a good rock. You hit it at the right angle. You practice. A skilled knapper is better than a beginner, but the skills can be learned by watching. Smelting copper from ore is different. It requires knowledge of which rocks contain metal. It requires building and maintaining a kiln that reaches specific temperatures. It requires understanding fuel, airflow, reduction chemistry, mold making, annealing cycles, and alloying ratios. That is not a skill you pick up by watching your neighbor. That is specialized knowledge passed down through apprenticeship, requiring years of training and a community willing to feed you while you learn. And once you have a class of people who do not grow food because they spend their time making metal, you have just invented economic specialization. And economic specialization requires surplus agriculture. And surplus agriculture requires organization. And organization requires leadership. And leadership over time becomes hierarchy. Copper did not just give humans better tools. Copper gave humans inequality. The Nahal Mishmar hoard, discovered in 1961 in the Cave of the Treasure in the Judean desert, contained 442 copper objects dating to the Chalcolithic period, roughly 4,500 to 3,500 BC. Crowns, maces, scepters, made using lost wax casting, a technique so sophisticated it requires multiple steps, wax modeling, clay molding, burnout, pouring, that the existence of these objects proves an entire organized social system behind them. Someone commissioned these. Someone made them. Someone used them as symbols of authority. The ability to work copper did not just reflect power. It created it. And copper created something else. War. Real war. Organized, large-scale, lethal war fought with metal weapons over metal resources. Before copper, conflicts between groups were limited by what stone could do. Raids, skirmishes, violence, certainly, but constrained by the fragility and availability of weapons. Copper changed the equation. A copper axe does not shatter on impact. A copper spearhead can be resharpened indefinitely. And the mines that produced the ore became strategic assets worth fighting over, the same way oil fields are fought over today. The Timna Valley in Palestine, modern-day Israel, was exploited by Egyptian mining expeditions during the New Kingdom. Roughly 1300 to 900 BC, temples dedicated to Hathor, the patron goddess of miners, were built at Sinai mining sites. The pharaoh's legitimacy depended in part on his ability to control copper. Copper was not just a resource. It was power. It was currency. Workers who built the pyramids at Giza were equipped with copper chisels, saws, and drills, thousands of them constantly resharpened or recast. Recent geoarchaeological studies at the ancient harbor near Giza found massive copper pollution in the sediment layers, evidence of industrial-scale smelting happening right at the construction site. The pyramids were not just built with stone, they were carved with copper. And without copper, they do not exist. Now, here is something most people do not know. Copper was not discovered once. It was discovered at least 3 times, independently, by people who had never heard of each other. In North America, around the Great Lakes, indigenous communities began working native copper roughly 9,000 to 9,500 years ago. That makes the old copper complex nearly as old as the copper working traditions in Anatolia. These people mined massive deposits of native copper in what is now Michigan and Wisconsin, cold hammering and annealing it into spear points, axes, knives, and awls. The copper was 99% pure. The tools were functional, heavy, and effective. But here's the difference. They never developed smelting. They never discovered that copper could be extracted from ore. For thousands of years, they worked exclusively with native copper, treating it as a workable stone. Around 1000 BC, the focus shifted from utilitarian tools to prestige jewelry, and eventually the tradition faded. An entire metallurgical culture, spanning thousands of years, that took a completely different path from the one the Old World followed. In South America, Andean cultures independently developed full copper smelting by roughly 1400 BC. They figured out extraction, casting, and eventually bronze alloying completely on their own, tied to ritual practice and social status. 3 continents. 3 independent discoveries. Same material, same basic chemistry, different timelines, different outcomes. And there is one artifact that connects the copper story across an entire continent in a single object. In 1991, hikers in the Ötztal Alps found the frozen body of a man who had died roughly 5,300 years ago. Ötzi the Iceman. He was carrying a copper axe with a yew wood handle bound with leather and birch tar. The copper was 99.7% pure. And in 2017, lead isotope ratio testing revealed something nobody expected. The copper did not come from the nearby Alps. It came from southern Tuscany, in central Italy, nearly 500 kilometers away. 500 kilometers in 3300 BC. Someone, or more likely a chain of someones, moved that copper across the entire width of the Italian peninsula and over the Alps. That is not casual trade. That is a network, an organized system of exchange that moved a valuable material across cultural boundaries, mountain ranges, and hundreds of kilometers of difficult terrain, 3,000 years before the Roman Empire built its first road. Copper was valuable enough to carry that far, and the man who carried the axe was valuable enough to someone that he had it, and copper gave its name to the very island that made it famous. During the Late Bronze Age, the island of Cyprus, known to the ancient world as Alatia, exported staggering quantities of copper across the Mediterranean. The Romans called the metal As Cyprium, metal of Cyprus, which shortened to Cyprium and then to the Latin cuprum. That is why the chemical symbol for copper on the periodic table is Cu. Every chemistry textbook on Earth carries a trace of an ancient island's copper mines in 2 letters. The Sumerians, thousands of years before the Romans, called it Urudu. And because Mesopotamia had almost no copper of its own, every piece of Urudu in every Sumerian tool, weapon, and ornament had to be imported from hundreds of kilometers away. The entire economy of one of the world's first civilizations depended on a material it could not produce locally. Sound familiar? And if you want to see what copper looks like after standing in the open for a century and a half, look at the Statue of Liberty. Roughly 31 tons of hammered copper sheeting, originally a shiny reddish brown when it was unveiled in 1886. Within decades, the surface oxidized, reacting with oxygen, water, and the salt air of New York Harbor to form a layer of copper carbonate, a green patina. The same chemical family as malachite, the green rock that started this entire story. The Statue of Liberty is, in a sense, slowly turning back into the ore it came from. And that patina is not damage. It is protection. The green layer seals the surface and prevents further corrosion. The same chemistry that made malachite beautiful made the statue durable. Now, here is one more thing about copper that connects the ancient world to tonight. Copper is antimicrobial. It kills bacteria, viruses, and fungi on contact through what is called the oligodynamic effect. Copper ions penetrate microbial cell walls, degrade DNA and RNA, and cause fatal oxidative stress. Ancient Egyptians did not know the chemistry, but they used copper vessels for water storage and copper compounds for wound treatment. The Edwin Smith Papyrus, dating to roughly 1600 BC, describes copper-based treatments for infections. They figured out the application 4,000 years before anyone understood the mechanism. And today, hospitals are installing copper touch surfaces on doorknobs, bed rails, and ivy poles because the same metal that ancient people hammered into beads 10,000 years ago still kills pathogens on contact. So, the answer: how did humans discover copper? They found it lying on the ground. Native copper, pure metal in nugget form, was spotted, picked up, and hammered by curious humans in at least 2 regions independently: Anatolia around 8,200 BC and the Great Lakes of North America around 7,500 to 7,000 BC, probably earlier in both cases. For roughly 3,000 years, they treated it as a special stone. Then, sometime around 5,000 BC, someone heating malachite, a green copper carbonate mineral used for cosmetics and pottery glaze, in a charcoal-fueled kiln with restricted airflow, accidentally created the conditions for a chemical reduction reaction. The carbon stripped the oxygen from the copper oxide, and pure metal appeared where no metal had been before. That is smelting. And smelting was almost certainly an accident, born from the intersection of 3 older technologies: pottery kilns, cosmetic pigments, and charcoal production. Nobody set out to invent metallurgy. They were trying to make nice-looking pottery, and metal fell out of the kiln. Was this a single discovery from a single source? No. The evidence overwhelmingly points to multiple independent origins. Belovode in Serbia shows copper smelting by 5000 BC, independent of the Near East. The Great Lakes tradition developed without any contact with the Old World. Andean cultures arrived at smelting on their own timeline. Given the chemistry, the probability that any culture with access to malachite, charcoal, and a kiln hot enough for pottery would eventually stumble onto copper smelting is very high, roughly 90%. The accident was inevitable. The raw materials overlapped, the temperatures overlapped, the only variable was time. But here is the part that stays with me. Copper is soft, it bends. It is not as sharp as obsidian, not as hard as granite, not as common as flint. By any rational assessment, the first people who picked up a native copper nugget should have tossed it aside. It was worse than stone by almost every practical measure, but it was strange. And humans do not throw away strange things. They hit them, they heat them, they carry them 500 kilometers across a mountain range. They grind up the green stone that contains it and paint their eyes with it. They put it in a kiln and accidentally invent an entirely new category of material. And from that single soft, reddish, impractical metal, humans built the first alloys, the first trade networks, the first specialist economies, the first organized armies, and the foundation of every industrial process that followed. Steel, aluminum, silicon, every metal and alloy on Earth traces its lineage back to someone, somewhere, staring at a strange lump in a riverbed and thinking, what happens if I hit this again? Tomorrow, you will touch copper. A coin, maybe. A wire inside the wall. The circuit board in your phone. You will not think about the woman who ground malachite into powder and painted her eyelids green 10,000 years ago. You will not think about the potter who opened a kiln and found bright metal beads where only green dust had been. You will not think about the smith who breathed arsenic fumes until his legs stopped working properly, or the traders who hauled copper across the Alps before the wheel was common, or the pharaoh who carved a mountain into a pyramid using a metal that bends if you squeeze it hard enough. You will just use it, the way you use everything that someone else figured out for you. And that is probably fine. But the next time you see a green rock, maybe pick it up. You never know what is inside it.